Hello, I'm Anatole, and my teammates are Christian Pabone and Nate Scuba. Together we worked on the analysis and design of a black powder cannon with our sponsor Mr. Charles Gray and our faculty advisor Dr. Shiki. For this project, we were tasked with analyzing a ceremonial black powder cannon and using the generated data to design a larger and improved version. This picture shows the original cannon, which was built by our sponsor when he was in high school. A senior design team worked on this project last year, however their results were inconclusive. Our objective was to take more accurate sound measurements, refine the impulse calculations, and design a new cannon with the following requirements. The new cannon should be 50% louder than the original in terms of perceived loudness. The bore diameter should be 0.75 inches compared to the 0.5-inch diameter of the original, and the new cannon will be made of 4140 low-carbon steel. Now to our testing. Our testing setup included a wood log that the cannon is aimed at in order to stop the projectile which is fired from the cannon, a digital chronograph which measures the speed of the projectile, a halogen lamp which allows the chronograph to function properly, the cannon itself, a steel pipe which acts as a guide for the projectile as we fired 6 feet from the chronograph, stones which shield the chronograph and stabilize the pipe, and an accelerometer to measure the acceleration of the cannon when it's fired. Test equipment we constructed includes an 8-foot-long rollback platform which minimizes the cannon's rolling friction and keeps it moving in the axial direction, as well as a charge press. The charge press was designed to compact the powder within the cannon to a desired force in order to consistently control this testing variable. On the right we see the components of this device. The load cell bracket was designed to connect the load cell to the charge press lever arm, which can be seen in the assembly image. We first measured the cannon's sound level using Rise Pro decibel meters, but collected inconsistent and incorrect data. We learned that this was due to a sampling rate issue with the decibel meters, so we obtained a higher quality TSI decibel meter to perform further testing, but we still ran into a sampling rate issue and we were not able to obtain reliable data.
Now we will move on to the results from cannon testing, but first, here are a few clips of the cannon firing.
ANSYS was used to simulate the maximum stress the barrel experiences during firing. Our barrel, which has a 1/2-inch bore, 3/4-inch barrel thickness, and 5.5-inch inner barrel length, experiences a maximum stress of just under 16,000 psi.
Here on the left is our testing data on how the speed of the projectile changes based on the charge mass used. As you can see, the speed initially increases with the charge mass, but then, because the barrel length is decreasing with more charge mass being added, the velocity of the projectile is reduced. Here on the right, we see a mostly linear relationship showing that the rollback increases as charge mass increases. The following material properties and equations were used to further our analysis of our testing data. First, we have the average pressure equation, which is derived from the impulse equation. This tells us the average pressure in the cannon for a given projectile velocity. Next, we have the peak pressure equation. This equation is derived from the average pressure equation and the ideal gas law. This gives us the peak pressure within the cannon for a given test, and it is this value that is used for the maximum stress equation. Our third primary equation is for the maximum stress on the barrel, which is a function of the inner and outer pressure and radius. This represents the hoop stress for a thick-walled pressure vessel. In this equation, we use the peak pressure to find the maximum stress, which is then used to calculate the factor of safety. Using the equations previously discussed, we find this graph of the pressure plotted against the charge mass. Intuitively, the pressure increases as charge mass increases, but then we see the peak pressure flatten due to the projectile velocity starting to decrease. However, this flattening effect is overcome by the increase in charge mass and decrease in barrel length. Using the peak pressure in the maximum stress equation, we find this graph, which follows the same trend as the peak pressure graph for the same reasons. However, the maximum stress is always higher than the peak pressure. Plotted against the calculated stress here is our ANSYS simulated maximum stress, which follows the calculations closely. Then on the right is a factor of safety plotted against the charge mass. These values are calculated from the highest stress values in each trial set. The factor of safety trend is simply the reflected pattern of the maximum stress trend.
We investigated the relationship between barrel length and sound levels by making 5-mile cannons out of steel pipes ranging from 4 to 12 inches in length. Last year's group also did this experiment, and we arrived at the same results, showing that sound increases as barrel length increases. The 50% increase in sound is perceived sound, so we need a 5 decibel increase, therefore making our new barrel 10 inches in length. Here's a short clip showing us performing the pipe experiment. Based on our data collection, to meet the new requirements, our new cannon will have a 3/4 inch bore, 1 inch barrel thickness, and 10 inch inner barrel length. Overall, the new cannon will be 7 inches in height and just under 2 feet in length.
When designing and determining new dimensions for the new cannon, we have to consider the factor of safety in two critical design elements. The first is the factor of safety on the barrel. Since it is not possible to determine the exact velocity of a projectile in the new barrel, we conservatively designed the barrel to comfortably operate at higher than peak velocities previously found in the original cannon, which resulted in a 1-inch thick barrel wall. The new barrel will have at least a factor of safety of 4.5 for velocities lower than 1,000 feet per second. The second factor of safety considered was that of the pins that hold the barrel in place. Again, since an exact velocity, therefore force, is not known, the pins were also designed to operate comfortably at 5,000 pounds of force, which corresponds to 1,000 feet per second projectile speed with our 1/2-inch diameter pins. The horizontal lines on each graph show the lowest estimated factor of safety.
The overall goal of this project was to collect data on our current cannon and safely make a larger cannon that is 50% louder. We had a lot of fun along the way, but also learned it is very difficult to measure the peak sound levels of cannons. Thank you for taking your time to learn about our project experience, and we hope you enjoyed.